Hi, my name is Olaf. My dashboard is about star classifications. So when you're observing stars at night, you find out different stars seem to have different colors. Some of them seem to be white, some of them seem to be red, and then some of them seem to be very bright, but some of them seem to be dim. So the question is, how can we classify stars based on what characteristics? And then is there any general trend for the stars to follow, or everything about stars are random? So I found this data set on Kaggle. There's a 240 data points total in this data set. And if you're interested, you can check out the original data set. And then on the right side, I have this little overview for the dashboards that I made. There are five dashboards in total. So the first dashboard is HR diagram, is a Hertzsprung-Russell diagram. So on the left side, as you can see, I put the URL link on these pictures. You can read more information on this website if you're interested. So this HR diagram is very important to understand this data set. On the for the x-axis, you can see this is about surface temperatures of the stars. So and it's a reverse relationship. Usually the higher temperature, the stars will appear to be blue, and then the lower temperature become red, and the in between will be yellow. But you will never ever see green stars because it's just physically impossible because of the structure of our eyes. And on the y-axis, that's luminosity. That means like how shiny, how bright the stars look at night. And then you can see here, this means 1. That means so all the data set and how they measure the luminosity is use the sun, our sun, as a reference. So I put FYI here. The luminosity of the average luminosity of our sun is about 3.828 times 10 to the power of 26. So this is the data that we use. They calculated as their luminosity, their solar units divided by our sun. That's how we get it. So if you're 1, that means your luminosity is exactly the same as our sun. And then on the right, I did this classifications based on different type of stars in this data set. So it's from 0, 1, 2, 3, 4, 5. Type 0 star, that's brown dwarfs. And then here there's the descriptions about different type of stars and their characteristics. So you can see main sequence. They're located like diagonally on this graph. And in reality, 90% of our stars, including our sun, is main sequence stars. And then you can read about it here about different type of stars characteristics. And then on the right side, I did a simulation to imitate the size of different type of stars based on their size, their radiums, their average radiums. You can play around it to see how different the sizes are. So as we know, the white dwarfs usually located here. That means they're very hot but very dim. Let's see, and then their size are very small. So they're usually 1%. Yeah, on the tooltip, you can see there's usually about 1% of the size of our sun. And then let's introduce brown dwarfs. You can see brown dwarfs are bigger than white dwarfs, but not a whole lot. And then let's add in red dwarfs. Red dwarfs is type 1. So red dwarfs is about 35% of the size of our sun. And then white dwarfs look very small compared to red dwarfs. And then main sequence. Main sequence is a lot bigger than any other dwarfs. And then supergiants. Supergiants usually very bright, and they're very large too. And then but their temperature is relatively low compared to their size. And then the last one is hypergiants. You will see hypergiants is way bigger than all the other stars. You see hypergiants. Hypergiants is about 1,367 times bigger than the size of our suns. So as you can see, you can't really see anything about the white dwarfs. The white dwarf is just so tiny that it disappeared compared to the size of hypergiants. I just say there's a filter here. You can play around. You can see the difference between white dwarfs and hypergiants. You can see how tiny the white dwarfs are. You can barely see it because it's just so small. Okay, the next dashboard. Next dashboard is about Harvard Spectral Classification System. And it's developed in 1901 by Annie Jump-Canyon. And I put a URL link on there too. You can read more information on Wikipedia. So what she did is to she classified stars in 7 different groups from type O, B, A, F, G, K, M. It's not very intuitive to memorize, but it's all you need to know is that it's based on the temperature and then color of the stars. And then it's decreasing on the temperatures, in the temperatures. And then usually hotter stars, they appear to be blue, like type O and type B, and then cooler stars, they are like orange to red or red, like class K or M. So on the left bottom here, I did the bar charts on the spectral class based on the temperatures. So you can see their temperature is decreasing because this classification system is based on the temperature. And then I counted the different type of stars based on the color in this data set. You can see most stars are like red or blue. It's a class O and B and A or class M, but this is only in this data set. But in reality, most of the stars are like a main sequence stars. So for my next dashboards, this dashboard is an explanation of this data set, and then is there any obvious trends that we can observe? So you can see this is a different type of stars based on each spectral class. We can see here, so in this data set, they choose 40 data point in each star type, but is based on the star type, not based on the spectral class, because you can see there's only one star that is belong to class G, and then but there are 111 stars on class M. So we can really draw an accurate conclusions based on this data set because we don't have enough data, but we can still see that there's some general trends we can probably observe. So here is the general trends. You can see this spectrum class G here, they're very high, but in reality, because it's mainly because they choose the class G and based on the hypergiants, so it's not really accurate, but still we can still see the general trends here. And as I mentioned in the last dashboard, so this classification is based on the decreasing under temperatures. So the general trends are the color correlates with the size and luminosity. So usually hotter stars, they tend to be bigger. You can see here this luminosity in the radiums. So hotter stars, the higher temperature stars usually burn brighter, and then their size are bigger too. And you can see that this actually follow the trends. So for my force dashboards, I want to explore the relationship between temperature and luminosity. So I run this 2 dashboards based on type 3 main sequence and the white dwarfs and the hypergiants. And then the data set, the data points, the size of data points is the radiums of the stars. And then the temperature, the color is based on the temperature. So the more blue you are, the higher the temperature is, and in reality it is the case too. So for the x-axis, that is temperatures. This is a reverse relationship. So the most common general trends in this in for type 3 main sequence is this mass luminosity relationship. So larger stars are generally more luminous because larger stars have much larger surface areas too, so they can emit more energies. So they will burn brighter, they'll be brighter. And then the larger stars also have more gravity crashing inwards, so to prevent from collapsing. And then you can see this main sequence do follow these trends, right? Because the radiums means, yeah, the size of this point means the radiums of the stars. They are actually a lot larger than when the stars are cooler. So I did this 2 annotations on here for the characteristics. So blue stars means hotter stars. So hotter stars are usually brighter and then also bigger because the luminosity, as you can see, they're way higher than this data sets. And then the red stars usually much cooler, and then they're small compared to the blue stars, and they're much dimmer too because they're like close to the bottom. And then for this dashboard, you can see they don't really follow. They're all types of sizes and all types of luminosity and all types of radiums. So they don't really follow the general trend. They don't follow the mass luminosity relationships, but there's some trends that we can probably observe. So white dwarfs, type 2 white dwarfs, you see how tiny these white dwarfs are. They're here. They're all types of white dwarfs. They're all different temperatures, but you can see they're very tiny and they're hot because their temperature is actually higher, much higher than the hypergiants over here. That's the relationship we observe. And then for hypergiants, all of these are hypergiants. You see they're very big. Their radius is much bigger than the tiny white dwarfs. So you can see here the blue and hot. The blue giants are usually blue and hot, and red giants usually cool and luminous. They don't really follow the mass luminosity relationships. And that's basically just explaining this 2 dashboard is just explaining the relationships between different type of stars. And then here for my final dashboard, so I put all the data set together and run simulations. You can observe whatever relationship you want to know. And then the general rule is that luminosity depends on the size and the temperature of the stars. And then with the same size of stars, the higher the surface temperatures of the stars are, the brighter the stars will burn. So you can use this filter over here. There's 4 different filters for you to observe if this data set follow the trends. So let's say, because they're so tiny, we can remove the hypergiants. Let's say if you want to observe main sequence, so remove everything, only main sequence, then you can check out their information there on their tooltips. And then these are spectral class AM. So these 2 are brown dwarfs and the red dwarfs. You can see, and then you use the filter here. Let's say you want to observe the same size of stars, so you want to move it very low. God, this is too small. These dwarfs are too small. Never mind. Okay, let's see the difference between the brown dwarfs and red dwarfs compared to hypergiants. You will see how tiny they are. And then they're extremely cold, right? Because you look at this here. And then you can explore the temperature if you want to. Let's say you only want to observe the temperature between 0 to 6,000 Kelvin. So you move this down all the way down to 6,000. And then here, then you can see this relationship. So basically use the filter to play around to see whatever you want to observe. This hypergiants, this is main sequence. And let's say right now you only want to see the luminosity that is less than 50,000. So you move that to 50,000. So boom, that's everything. So you can just explore it to see if the general trends are correct or not. Okay, that's my dashboard. Thank you for listening.